Next part of looking at locus, and it's looking at functions then. So omega equals some function of z. And then we just have to find what is the locus of. Now sometimes they ask us for omega, sometimes they'll ask us for z, but I guess the key is they're going to give us some condition for omega or z. Make that condition the subject is usually the key to solving these problems. So whatever the condition is, make that the subject and play around with that. Some key things to look at. If you see this, the condition is they tell you this complex number is purely real, then the idea that we could use, well, there's a couple of ideas. We could use the fact then that the imaginary part is equal to 0. And that's probably if we're going to go down some algebraic approach and we go and solve something on that. A geometrical approach, we'd look at the argument. So we say, well, if it's purely real, then the argument must be 0 or pi. And then we play around with that. A similar one is if it's purely imaginary, then the algebraic approach, it'll be the real part is equal to 0. Play with that. The argument would be either plus or minus pi on 2. So that can be useful. This particular situation, argument of, and then inside there you get linear function on linear function, so that z minus some complex number over z minus some complex number, and it'll be equal to something. That will always turn out to be an arc of a circle. Won't be the complete circle, but it'll be an arc of a circle. So if you see that, we can recognise and we know, that's going to be the arc of a circle. It'll turn out to be a minor arc if that angle is bigger than pi on 2. It'll turn out to be a major arc if that angle is less than pi on 2. So consequently, if it is pi on 2, we'd have a semicircle. So there are a couple of key things to keep an eye on. We'll get a question like this then. We want to find the locus of w, and here's our function. W is z plus 2 over z, but the condition is the modulus of z is equal to 4. Now what are we doing here? Our problem is we live in a three-dimensional world. And that was all right when we were just playing with real numbers and functions and we want to have a picture of the function. Because I substituted in usually an x value, I got a y value, I could plot the point in 2 dimensions. But now, what we're substituting in actually has 2 pieces of information in itself. Remember, our Argand diagram we're using to represent actually a single number, but we're using 2 dimensions to represent that single number because it's got a real part and an imaginary part. So that's what I'm substituting in, but I'm going to get out another complex number which will also have 2 parts. I now have 4 pieces of information to plot. Well, how do you do that in 3 dimensions? You can't. You need 4 dimensions to do that. So what we do with this is a little bit different. It's like we have 2 different Argand diagrams, and one Argand diagram will represent the input and one Argand diagram represents the output. And that allows us then to have 4 pieces of information using 2 separate ones. So what we're doing here is we want to find out what this input would be if the output produces complex numbers that are on this circle z equals 4. How to approach it? Well, we want to make z the subject because the condition we've been given is on z. So let's play around with this and make z the subject. Multiply both sides by z, factorise, divide, I now have this. Now why I do that is because I know the modulus of z is equal to 4, so I can now say, oh, well then the modulus of 2 over w minus 1 is equal to 4. And now I can look at this and say, well, what's that? If I play around with that one, well, modulus of 2 is of course 2. We get this, and we recognise that to be a circle as well. So our locus is a circle. Its centre is 1, 0, radius is a half. In other words, it would be this particular circle here. This is what we're basically doing. We've got 2 Argand diagrams. One's the input, one's the output. Now, we're inputting all these complex numbers that are on the circle, and its radius is 4. So we're saying we're going to get every point on that circle, we're putting into that function, and what will we get? We will get another circle, but this time the centre's at 1, 0, the radius is a half. If we could have a 4-dimensional picture, we could put that all together and we'd come up with some 4-dimensional shape. But obviously in 3 dimensions, which is what we live in, we can't do that. So this time I'm told W is Z plus 1 over Z minus 1, and the condition I've been given is that W is purely real. Okay, do I want to go an algebraic approach? Do I want to go a geometric approach? Well, let's do both just to see how they differ. So the first one, I'm going algebraic. So I move everything into real and imaginary parts. So I want to realise the denominator and play around with that. Oh my goodness. I'm not going to expand the whole thing out because I'm only interested in the imaginary part. Because I know if it's purely real, the imaginary part is equal to 0. So in fact, I don't really care about the denominator either. So I've got a fraction equaling 0. It's got to be the top of the fraction. So I'm really just looking at the imaginary part of the top of the fraction. That's going to equal 0. So I know minus x plus 1y plus x minus 1y is equal to 0. Eventually, okay, it just comes out to be simply y equals 0. So there's our locus. But of course, remember, you've got to go back to the original question and see, hang on a sec, is everything included? In this case, 1, 0, that particular point wouldn't be included because you can't have 0 on the bottom of a fraction. So I couldn't substitute in the number 1 into that and get an answer. So the locus is our lovely line. It's our x-axis, but excluding the point 1, 0. Geometric, how would I approach it? Well, now I'd look at it and say, well, look, if it's purely real, then I know the argument is either 0 or pi. So the argument of z plus 1 on z minus 1 is either 0 or pi. So the argument of z plus 1 minus the argument of z minus 1 is 0 or pi. What is that telling me? Well, both of these arguments, if I put them on the same diagram, one of them would start at -1 and one of them would start at 1. And we're saying the difference in the arguments, so any ray I would draw from these points, the difference in them is either 0, so they're going in the same direction, or pi, so they would be going in the opposite direction. So I do get a straight line. But what would our straight line look like? Well, there's two pieces of it. That would be if they're in the same direction. So that's where the argument of z plus 1 minus the argument of z minus 1 is equal to 0. You see something like that where the argument minus the other argument, you know it's going to be collinear. If the difference is 0, then it's going to be on the outside of the 2 points. Of course, if it's pi, whoops, went the wrong way, we're going to be on the inside, but I have 2 points of exclusion. Oh, hang on. The first one said there was 1 point of exclusion. The second one says there's 2 points of exclusion. Which one is correct? Well, again, you always go back to the original question. We say, well, look, I've changed this into a geometry problem. So in my changed problem, I'm excluding these 2 points. Let's go back to the original one and see if that is in fact true. If I substitute in 1, yeah, it doesn't work. Well, we know that from the other one. But if I substitute in -1, what do I get? I'll get 0 on the top of -2, which is 0. Is the number 0 a purely real number? Well, yes, it is. So I do include that one. Now that's the difference. If the question I was answering was simply this one, that the argument of z plus 1 on z minus 1 equals 0, then yes, there would be 2 points of exclusion. But that wasn't the question. I changed the question to that so I could solve the problem. Always go back to the original question. Alright, let's have a look at one like this. This is the one where if I see it, I know I've got an arc of a circle. So I've got the argument on the top, I've got z minus some complex number, in this case it's 0, and on the bottom I've got z minus some complex number, which in this case is 4, and it's equal to pi and 6. So I know I've got an arc of a circle. Because what I'm really saying then is the argument of z minus the argument of z minus 4 is pi on 6. So the difference in these arguments is pi on 6. Let's draw ourselves up a little picture then. One of the rays is going to start at 0, one of the rays is going to start at 4, and the angle between these two will end up being pi on 6. That will end up being the difference. Now you might be looking at that and think, well, why have you drawn the rays in that direction? Well, that's because I've already done something. Reality is I probably would have drawn them up. I would have said, oh, imagine z's there. There's my 2 and the angle is pi on 6. But I know the argument of z minus the argument of z minus 4 is pi on 6. Now if that's theta and that's alpha, so there's the two arguments. Theta minus alpha is pi on 6. That's what we're basically saying there. So theta is pi on 6 plus alpha, but have a look at my picture. It's the exterior angle of a triangle, so how is theta bigger than alpha? Can't be. Therefore, I'm not above the axis. I must be below, and I'm dealing with negative numbers, and that's why that statement then can become correct. So the reality is I probably would put in the positives first and then investigate and see, oh, hang on, that doesn't work. Therefore, I'm below. So it's below the axis basically because the argument of z has to be bigger than the argument of z minus 4. Now, I know it's an arc of a circle that's going to go through these 2 points and also the point of intersection because that's where they meet. Now, I need some circle geometry to do this. You see, the line joining 0 and 4 must be a chord of my circle. And we know the perpendicular from the centre will bisect the chord. So finding the midpoint of that chord is going to be useful because to define my locus I'm going to need to know where the centre is. So I'll plot that in. But it's the perpendicular from the centre that bisects the chord. So I know if I draw at right angles to that I will pass through the centre. Now, because it's a major arc, because it's pi on 6, I know the centre must be in the same half as that point of intersection. If it was a minor arc, then it would be on the centre would be on the other side. So I know I'm down there. It will have coordinates 2 and some y value. I now have to try and find what the y value is. The radius is obviously that distance there. Once I know the y value, I'll be able to work out the radius. The next bit of circle geometry we have to remember. The angle at the centre is twice the angle at the circumference. So the angle at the circumference is pi on 6, which is 30 degrees. Therefore, in that triangle, it must also be 30 degrees because the whole thing is twice the angle. So they bisect it, I get the same angle there. Okay, a little bit of trig. Y on 2 is tan 60. I'm not worried about the negative sign at this stage. I know it's going to end up being a negative number because it's below. But y is 2 root 3. So actually it's negative 2 root 3 because it's below. But I know the centre is negative 2 root 3. This now allows me to find the radius. Radius will be 4. I can now describe my locus. There's a mouthful. It's going to be the major arc of that particular circle. It's going to be formed by the chord that joins 0, 0 and 4, 0, but not including those points because that's the start of the ray. That's how I could write that. I suppose another way I could do it, rather than saying formed by the chord joining, I've still got to say it's the major arc of that circle, but I could write it something like this. So it's the major arc of the circle, x minus 2 squared plus y plus 2 root 3 squared. And I know, because it's below the axis, that the y will always be less than 0. So that would, I guess, be another way of describing that and saying, okay, this is the picture that we're talking about. Okay. So, in our textbook, we got 1F. I've grabbed one from Patel as well. And there's a sheet there with a handful of past HSC geometrical complex number problems.